Our next speaker is Alex Hall. He's a professor here in AOS. He is the director of the Center for Climate Science, and his interest is in both global scale and regional scale climate change. And in particular, he is interested in how to downscale information from global climate models to the finer scales, which are more of interest to society. And he has applied these ideas to the Los Angeles basin and to the Sierra Nevada region, which is probably a really important topic these days because of the water situation here in the Southwest. And he has some interesting things on UCTV, University of California TV. And one of them is entitled, "What Does Climate Change in the Sierra Nevada Mean for Us?" And then another one is on LA's Climate Future. I think there's the title of that one. So his talk today is on sub-seasonal clustering of atmospheric rivers in the western U.S.
Okay. Well, thank you for that introduction, and thank you to the organizers for inviting me. Even though I don't work directly on the tropical circulation and convective and turbulent parameterizations, I did stumble upon something recently that I think would interest Akio, would have interested him quite a bit. This is with a postdoc of mine, Emily Slinsky, and a researcher, Naomi Goldenson, which is this evidence that we have now that there is clustering of atmospheric river events, that they don't actually happen randomly, that they actually are sticky in time. And I wanted to just, in this short talk, present that evidence. And I don't think I have to convince you that atmospheric rivers are important. Obviously, they're key for water resources in California, and they also pose very significant flooding risks. But I wanted to just show you a time series of a water year in Los Angeles, which is 2004, 2005. This was like about 3 years after I came to UCLA. And this is beginning in December here on the left, and then proceeding to the right and ending at the end of February. And what's being shown is precipitation, and also these vertical bars are atmospheric river events. And there was a few atmospheric river events that happened in early January, and then there was another cluster of them that happened in mid to late February. And I actually just had some family members that visited me. I invited people out to visit. About 10 people stayed in. I just bought a condo. About 10 people were in my condo, so it was pretty tight quarters. And they arrived at the beginning of this event. They left at the end of it, the end one. And so it basically rained for about 10 days in Los Angeles. My sister, so we're all cooped up in this condo. And you can see there's a little bit of a place where there was a little bit of a lull, and my sister left in a huff with her kids to go to Disneyland, but of course it started raining again. It was just this continuous rainstorm. And then, I had a hard time persuading them to come back to visit me. I would say, "You should come back and come back to Los Angeles," and they'd say, "No, it's too rainy there." So I have a personal interest in these clusters. Anyway, I just wanted to show you just a visual of this sequence for this water year. So you can see pretty clearly that these events seem to have a clustered behavior. Now, of course, this is just 1 year, and you could argue this is just the mind trying to see a pattern. So we'll examine that assumption in a moment. I also wanted to connect this to some interesting statistics about precipitation in the US that have been compiled by others. This comes from a plot by Mike Dettinger and Dan Cahan, just showing you a simple statistic of precipitation in the US, just taking the standard deviation, dividing it by the mean. So how variable is precipitation on an interannual basis compared to the total amount of precipitation? And the whole eastern third of the US is super boring. Basically, it rains very consistently every year. And I was reminded of that a little bit yesterday when Carrie showed that global tropical cyclone statistic where we have 90 of them every year, and they vary a little bit, but not that much. And that's kind of what the precipitation is like in the eastern US. Then you go further west, and even into these desert areas that are very arid and have very low mean values of precipitation, there's still actually quite a lot of consistency from year to year. So this metric is actually quite low. But if you look at California, it really just blows up. And there's just huge variation from year to year compared to the mean values. So there's really, there's just bizarre statistics of precipitation in California. And this has been attributed to the fact that occasionally we get big atmospheric river events, but they're rare. And so just by rolling the dice on rare events every year, you're bound to get variability. An alternative explanation, which I actually think is more convincing, is that we have anomalous clustering of just normal-sized atmospheric river events, that they cluster together, and when you have an anomalously large number of these series of clusters, you get a big rain year. But if you happen to be in a year where there are large, in the long intervals between the clusters, then it ends up being a very dry year. I wanted to just show this to highlight that we're trying to explain something strange about the statistics in California. We're going to be quantifying this temporal clustering of atmospheric rivers, just asking the question whether this is random, whether the patterns that we saw in that 1 year are just our mind trying to see something, whether this is actually statistically detectable. And then I'll be just showing you some statistics of these clusters and how they actually behave, and then looking at the connection with precipitation. Just to describe these methods, so we first have to have a way of detecting atmospheric river events, and there are a number of algorithms out there, but the one that we are using is the Guan and Walliser method, and this is basically where you just take the IVT at any given moment, and you have a threshold for the above which you must rise to detect an atmospheric river. And then you have geometric and directional requirements, so they have to be actually flowing in the right direction. And the data set that we're using for this is the ERA5 reanalysis. And on the left, you can see an atmospheric river and the IVT and the associated IVT threshold, which is in green, and that's what we're using to detect an atmospheric river. And then we have a dynamically downscaled reanalysis-driven data set that we're using for precipitation. This is a 9-kilometer WRF downscaling from ERA5, and I'll just note parenthetically that this has been evaluated against observationally based products like PRISM, and it stacks up pretty well against those products. So you can think of this as like the observations of precipitation, even though it's a downscaling from reanalysis. And then we have a method for detecting this clustering, which I'll just sketch out here quickly. We use a function called the Ripley's K function to quantify clustering among atmospheric river events along the time axis. And the basic idea is it's pretty simple. You just quantify how many events occur on average within some specified time interval of an event for a particular season. And then you produce a large number of Monte Carlo simulations with the same average event density as the observed time series, and I'll refer to this as the synthetic time series. And in this Monte Carlo simulation, the intervals between these events are drawn from a Poisson distribution. So it's the same number of events, and they have the same density as the observed time series, but they are not clustered in any particular way, except maybe by chance. And then we compare the observed degree of clustering to what is expected by chance. And if the observed degree of clustering falls in the top 5% of the values associated with the synthetic distributions, we consider it to represent significant clustering. So here's an example for the heart of the wet season in Los Angeles. And every circle here on the left corresponds to one of the 41 years that we used in this analysis. And then on the x-axis, these are just different aggregation periods. So we're just looking at clustering over longer and longer periods of time and asking whether the time series for that particular year is significantly clustered. And if it is clustered compared to the synthetic time series, we color the dot purple, or maybe it's red on there. And if it's not, we just leave it black. And then and again, the clustering is the 95% confidence level. And then the blue line on here shows the fraction of years that exhibit clustering at this 95% confidence level. And we expect roughly 2 out of these 41 years to be clustered. So we expect that this blue line should fall somewhere at this 0.05 level. But if you look at this blue line, it actually goes way above that. And in fact, if you look at these time scales that are shorter than about 20 days, you can see that something like 60 or 70% of the years are significantly clustered at the 95% confidence level. And then as you go to longer time scales, they're still clustered, but they're just not quite so significantly clustered. So we defined a threshold about if half the years are significantly clustered, then we denote that as a time scale of aggregation that is significant. So in Los Angeles, there seems to be this kind of 20-day time scale where you can have a lot of clustering of atmospheric rivers. And if you think back to that Los Angeles time series, which I have up here again, you can kind of see that in the data. This is actually a very typical time series for Los Angeles. All right, so what about some other places? If you look at, we know atmospheric river activity is very dominant all along the US West Coast. So if we do a kind of a transect and look at these same statistics for 3 different locations, one is in Portland, Oregon, that's the northernmost location, and Bodega Bay, which is just north of San Francisco, north of Point Reyes National Park. And then on the right is the plot that I already showed for Los Angeles. We can compute these same statistics. And if you look at Portland, it's also significantly aggregated, but it's on much shorter timescales, and the aggregation drops off also, but it's really at a timescale of maybe something like 5 to 7 days. And the Bodega Bay one is the one that kind of blew my mind. It's very clustered at very long timescales, and if you again take this threshold of half the years denoting significant clustering, being a threshold for this aggregation period being significantly clustered, it goes out beyond a month of significant clustering at Bodega Bay. And then the LA one is the one we've already talked about. So we can plot this significant aggregation period. It's this maximum time that we have clustering. So for Bodega Bay, it would be 35 days. And we can plot that, and that's what's shown on the right. And we can see for much of California, we have clustering of these atmospheric river events of somewhere between 20 and about 35 days. And then up in Oregon and Washington, there's also clustering, but on a shorter time scale. All right, so we can then identify these clusters, and you can do this. This is a subjective process, but it turns out it doesn't matter too much how you do it. We can identify these clusters by imposing criteria relating to the minimum gap between atmospheric river events, and this is guided by the results of the aggregation timescales that we found to be significant. So if you impose these criteria, you can actually identify the clusters, and we did this for this particular time series, and we identified 2 episodes with this algorithm. And so I think it's pretty reasonable, intuitive, that there would be these 2 episodes And then we could start to, once we've identified these episodes, we can then look at their characteristics. So one natural question is, how often do these clusters occur? And so on the left-hand side is just the cluster frequency, just the number of the total count of clusters in this 40-year time series. And you can see up on the coast of Oregon and Washington, there's a pretty healthy population of these clusters, but also in Northern California, the northern third of California, there's a very large population of them, and actually it's quite large, extending all the way down to Southern California. So these things are happening at least a few times a year along much of the coast of California, and probably a little bit more frequently in Washington and Oregon. And then another question is, on average, how long do they last? And this is the duration in hours, but you can convert that to days. In California, these clusters tend to last on average about 15 days. In Oregon and Washington, they tend to be a little bit shorter. And then we get the longest durations, again, in this area north of San Francisco, stretching about 100 miles north of there. Okay, another question is, how important are these clusters for the total amount of precipitation that these areas receive? So you can just divide the amount of precipitation associated with these atmospheric river clusters by the total precipitation at any given location. And it turns out in California, they're accounting for about half on average of the total amount of precipitation. So the clusters are really contributing significantly to the total amount of precipitation. And in addition, they're also tightly associated with extremes. So if you just look at the fraction of extreme precipitation that's associated with these clusters, it's actually very high. And in California, on average, about something like 60 to 70% of the extreme precipitation is associated with these clusters. So they're actually quite significant in terms of their impacts. So just some conclusions. Atmospheric rivers cluster at a rate that's significantly different from what we would expect by chance across the western U.S. And there's a pattern associated with it. We have these longer aggregation periods in California, somewhere between 2 weeks and a month, compared to the Pacific Northwest, where we have shorter aggregation periods. And we looked at this case study of Los Angeles. I just alluded to that. They have big impacts on human and natural systems. And this clustering occurs all on the US West Coast, but it's most frequently found across the northern third of California, as well as across the Central Valley and the Washington Cascade Range. The clusters contribute most of the precipitation throughout all of the state of California, with the largest fractions, again, over the northern third of the California coast, and also the Southern California transverse ranges are heavily impacted. And we have yet to test this thoroughly, but I think it's likely that this clustering is at least partly responsible for the unusually large interannual variability in precipitation in California. So next, we'd like to look at the large-scale environments and mechanisms that are responsible for clustering, and we've been working a little bit with David in this to advance this a little bit. And we want to also understand how well GCMs are actually simulating these cluster characteristics and the precipitation associated with them. Also, there are many other regions of the world that are affected by atmospheric rivers, so a natural question is to what extent are atmospheric rivers in other places also clustered? And what's their behavior in a warmer world? So lots of questions, I think, especially around the mechanisms that generate this peculiar behavior. But atmospheric river events just do not seem to be hitting us randomly. They seem to be clustered. So that's the main message. Thanks.
Thanks, Thanks, Alex. We have time for some questions?
Thank you very much. Very interesting talk. I was just wondering if you can talk about the mechanism a little bit. Especially, I was wondering if you had a cluster, does the first one have trigger the second one, or is it just the environment conditions that favor a lot of atmosphere altogether?
Yeah, I can only speculate about that. But I think a natural place to look is the tropical Pacific, and because we know that there is a relationship between precipitation, at least, and precipitation amounts, and tropical Pacific conditions, and I think it would be interesting to look at the life cycle of atmospheric rivers when they're spawned in the tropics, and what the conditions are when they're spawned, and I think that might be related to, for example, the El Nino phenomenon, or ENSO, and the different flavors of ENSO. So I think it would be interesting to try to tag these events by conditions in the tropical Pacific and see whether these clusters are related to that. But yeah, my guess is that they are. It's more the environmental conditions that are setting up favorable situation for clusters rather than them actually influencing one another, but I could be wrong. And yeah.
Yeah, Gary, want to take the mic?
Thank you. Alex, there you mentioned that you're using fairly high resolution sort of downscale to detect these. I don't know much about it, but there are these so-called 20th century reanalyses that go back well into the 19th century now. And if you thought that these rivers might be detectable in those, it would be interesting to try to go back that far for a record of clustering.
Yeah, we have taken this particular run back to 1950, this particular one, so we have now about 70 years of data. But I think even with the 40-year time series that we have, that the statistics are robust enough that...
I was thinking about climate trends.
Oh, yeah, okay, yeah. Yeah, that's a very interesting idea too, and that also might be a more useful time series for the predictability question too, because there you really do need more ENSO events and much more robust statistics. So that's an excellent idea. Thanks.
Yeah, Kim,
So, kind of related, a comment on the first bullet of good predictions. I think you heard about an old name for a Pineapple Express, because it was so stable in old days that you can use the flow of air to import pineapples from Hawaii. That's why it's called Pineapple Express. But as you said, climate is changing, so it fluctuates badly. So you cannot rely on that to import pineapples. My point is to figure out why this is happening and why it's changing. I have a personal kind of idea, trying to take advantage of tele-connection indices, because climate change means the large-scale patterns are changing. So if you, for example, calculate PNA, MJO, then you kind of figure out how pressure patterns are changing. Of course, you can include a jet stream. Then from some kind of regression formula, taking advantage of those indices, probably you can get an idea about why and how the larger scale environment is changing. So I thought about this for some time, but I couldn't work on it because I'm not in R&D work right now. But feel free to use it and let me know.
Yeah. Okay. Again, I think there's a lot of work to be done here to relate these clusters to the larger scale conditions and as you said, it may go beyond may go beyond what I mentioned earlier, the tropical Pacific, to include some of the modes that you also mentioned. So, yeah, thank you for that suggestion.
Okay, let's thank Alex again.